Okay, so we're going to take a look at question 19.3 from that batch of questions that I sent out to you this morning on Google Classroom. Also sent them in your email. And it reads the following. An experiment was carried out to measure the amount of temporary hardness and permanent hardness in a sample of water. A 50 centimetre cube sample of water was placed in a conical flask and some buffer solution and solid-chrome black tea indicator added. Now at this stage, it's important to say that solid-chrome black, as I told you before, is just another, I suppose, industrial name for the same chemical that we used in school called eriochrome black, so they're both the same. On titration, with 0.01 molar EDTA solution, the average titration figure was found to be 11.5 centimetres cubed. The water was then boiled for a few minutes and allowed to cool to room temperature. The titration was repeated and the average titration figure was found to be 6.5 centimetres cubed. Now, just before we go into the questions themselves, to make sense of that paragraph, number one, we're using 11.5 centimetres cubed of 0.01 molar EDTA solution against a 50 centimetre cube sample of tap water whose calcium concentration we simply don't know. We also know that from our previous questions, the relationship between calcium and EDTA is 1:1, so therefore we don't have to worry about N1 and N2 in our equation. But what we also see at the very bottom is that when we boil the water and allow it to cool, the average titration figure drops down to 6.5 centimetres cubed. Now there's a reason for that, and that's because water, by its very nature, hard water by its very nature, can be made up of two things. So the total hardness in water is made up of two things: permanent and temporary. Now, it's only the temporary hardness that can be got rid of by boiling. Permanent hardness stays. So if we take the figures that we have there, 11.5 centimetres cubed, when boiled, dropped down to 6.5 centimetres cubed of EDTA needed for titration. That there would be our total, and that would be the permanent. So I'm just aware of the question down number part 3, so our part C says it wants the total hardness and the permanent hardness and the temporary hardness in the sample of water. So this is the only reason I picked this question. So again, let's take the questions. Part A. What was the purpose of boiling the water? The purpose of boiling the water was to remove the temporary hardness. So when we heat water that contains temporary hardness, due of course to the fact that we have calcium or magnesium hydrogen carbonate. And we already know that the hydrogen carbonate gets into solution through that process we talked about. Carbon dioxide through the rainwater forms a dilute solution of carbonic acid. Carbonic acid then going through a limestone region forms calcium hydrogen carbonate, which is soluble in water, and that's carried then in the water system right through. If there's no treatment process beforehand, if you're taking the water from a well, that calcium hydrogen carbonate will end up in your house. And if it ends up in your house and you heat the water through your kettle or your immersion or your pipes, it will reverse that process, the natural process, throwing back out the carbon dioxide, throwing back out the water, and throwing back out the calcium carbonate in the form of limescale, which of course does damage to anything that contains hot water. So, part B. Why is it necessary to allow boiled water to cool? It seems like an unusual question, but if you think about it, when you heat anything, physics tells us that it expands. So therefore, if we're boiling water, the water at 100 degrees or 90 degrees has a greater volume than the water would have at room temperature. So therefore, if we were taking the water at a hot temperature, the volume would be incorrect. So we've got to allow it to fall to room temperature simply for the reason that we want the volume to be correct when we're doing our titration. And then of course number 3, calculate the total hardness and permanent hardness and the temporary hardness of a sample of water. Well, we've got two things we can work with. First of all, we're taking EDTA and we're titrating it against tap water, which we know has a certain amount of calcium or magnesium ions. We know that the volume and the molarity and the volume and the molarity change before boiling and after boiling. So we'll worry about that in a moment. Before boiling, the volume of EDTA that was required was 11.5 centimetres cubed and its molarity from the question 0.01. The amount of tap water, 50 centimetres cubed. And we have no idea of the amount of calcium. As I told you before, N1 and N2, we don't need them for the very simple reason that they're 1:1, so we don't use them in the calculations. So that's 11.5 times 0.01 is equal to 50 times x, which means x would be 11.5 by 0.01 all over 50. And that would be, if I think about that very carefully, 2.3 by 10 to the power of minus 3 moles per litre. Now I didn't do that in my head, obviously. I did it in a calculator just before I came online, so I have the answers ready to go, not to waste time. So that's what we have in relation to the water pre-boiling. So therefore that figure is the total hardness. Now notice it doesn't say anything about ppm, milligrams per litre, moles per litre. It just says calculate the total hardness, permanent hardness and temporary hardness. But because it's a natural phenomenon, it's a biological phenomenon, we have to give our answer back in parts per million. So we do know all hardness is due to calcium carbonate, which has a molecular molar mass of 100 grams. So therefore 2.3 multiplied by 10 to the power of minus 3 moles per litre multiplied by 100 grams is equal to 0.23 grams per litre. And if I want to go to ppm, I take the 0.23 grams per litre, I multiply it by 1000, and that gives me 230 parts per million. And it's important for a question like that to give the answer in parts per million. Okay, let's go to the other one where we have 6.5. So the only change again is that we still have our EDTA versus our tap water. But this time EDTA stays the same. So EDTA drops to 6.5 centimeters cubed for the volume. I should say the molarity stays the same, 0.01, and then the tap water is still 50 centimeters cubed, and its molarity is unknown because of the fact that we've boiled it. So in this case here, same kind of calculation again. 6.5 by 0.01 is equal to 50x, which means that x is equal to 6.5 by 0.01 over 50. And again, to save time, I have that already done. It's 1.3 by 10 to the power of minus 3 moles per litre. Now, again, don't give it back like that. Give it back in parts per million. So the first thing we've got to do is remember, again, CaCO3, we had it there. CaCO3, 100 grams is the smaller mass. We multiply this by 100 grams to go from moles per litre to grams per litre, which is 0.13 grams per litre of CaCO3. And to go to ppm, multiply it by 1000, because ppm is really milligrams per litre, which will give us 130 parts per million. So what do we notice? Before we boiled, 230 parts per million. After we boiled, 130 parts per million. What's the conclusion? We lost 100 parts per million. Where? To the disappearance of what we would call the temporary hardness. So to answer the questions, number one, we'd say that the total hardness is 230 parts per million. Number two, that the permanent hardness, that's what remains after boiling, has dropped 130 parts per million. So therefore, by very simple subtraction, the temporary hardness in the sample of water is 100 parts per million. And that's the question finished.